Today we have Professor Wang from USC. He did his, actually I'm very grateful to him. He was working at MIT. The point that our STC was actually reviewed to see whether we should get the money or not. And Hong was partly responsible for getting us the cash by giving a very friendly interview with NSF reviewers, panel members, and the like. He worked with Jing Kong and Tomas Palacios as a grad student at MIT on new materials, transition metal dichalcogenides and things like that. Then he went to IBM Watson for a year with Thaden Avarice, finding out how they do things with big money in industry, and then moved to USC. He's going to tell us about some remarkable new materials that look like sort of a tin roof, as you can see here with the straight gutters going in one direction, but not the other, which is sort of remarkable that it holds together, even that it conducts electricity, but has very nice properties. Look forward to hearing what you have to say.
Yeah, thank you very much, Bob, for the introduction. So it is my pleasure to visit Harvard and the Center for Integrated Quantum Materials. So in this talk, I would like to discuss our recent work in developing new type of electronic and photonic devices based on the emergent family of low-symmetry two-dimensional materials, especially focusing on materials like black phosphorus, but I will also talk about a few other materials we are working on along the way. So the nature has given us a large family of two-dimensional crystals from graphene to boron nitride to the transition metal dichalcogenides family and other compounds, which all have this layered two-dimensional structure with strong covalent bonds in plane, but only very weak van der Waals coupling between the layers, giving rise to this kind of almost ideally self-passivated material structure that's very attractive for developing new type of applications in electronics, in photonics, and also in their interaction with biological systems. So here I would like to show you two spectrons that are important for applications in nanoelectronics and nanophotonics. So the first is what we call the electronic spectrum. So you basically, we plot the mobility of different nanomaterials as a function of the on-off ratio of the transistors that can be demonstrated based on these materials. And different regions of this spectrum correspond to some unique applications in the field of nanoelectronics. And the second is the standard electromagnetic spectrum that's important for the photonic applications. So let's take a look at where the existing 2D materials sit on these two spectrums. So the first 2D material we start to work on is, of course, graphene. And graphene has a very high mobility. However, because of its zero band gap nature, the graphene transistors typically have low on-off ratios, right? That makes the graphene transistors only suitable for some very specific applications in RF electronics. It's not good for digital logic applications, for example, in general, right? On the optics side, the graphene can cover a very broad spectrum range, all the way from terahertz all the way to UV, right? If you were to use the material for sort of more passive type application, like detectors or modulators, but graphene is not a good material for light generation purposes. It doesn't make good LEDs. It doesn't make good lasers, right? For those applications, you need other 2D materials to fill in the spectrum. Now, on the other extreme, we also have the hexagonal boron nitride, which is a 2D material with a band gap of around 6 electron volts, and making the insulator, so you don't see it anywhere on this electronic spectrum, but its band gap corresponds to a narrow region in the UV spectrum range. And in the past few years, we have also seen the intense interest in the transition metal dichalcogenides family of 2D materials, with materials like molybdenum disulfide, tungsten diselenide. These materials typically have relatively lower mobility compared to materials like graphene, typically on the order of 50 to 100 centimeters square per volt second. But transistors based on these materials show very high on-off ratios, and that's mainly because of two reasons. Firstly, the sort of two-dimensional geometry of the channel allows the excellent electrostatic control by the gate over the carrier flows in the channel, and also the band gap of this material are typically relatively large compared to materials like silicon. So that gives rise to a high on-off ratio in these transistors. We have seen molybdenum disulfide transistors with on-off ratio on the order of 10 to the 8, 10 to the 9, and even 10 to the 10, making them kind of attractive for developing some sort of thin film or flexible electronics application that can run at the very low power consumption, especially in the off state, low power. And on the optics side, these materials typically fall into the visible spectrum range, and some of them goes into the near infrared. So if we take another look at these two spectrums, it's pretty clear that we still have some missing gaps here, right? So, unfortunately, these missing regions corresponds to some very important applications in both electronics and photonics. This regional trade-off, between mobility and on-off ratio of the transistor is sort of very useful for developing high-speed kind of flexible electronic system that can work into the gigahertz frequency range, while the incumbent industrial technology that's based on organic semiconductors still in the kilohertz frequency range. And this missing gap in the optic spectrum corresponds to the strategically important infrared region, from near infrared to mid-infrared to far infrared, and there's many applications in military, in communication, and also in medicine. So the question is, how can we bridge this gap? Basically, we need to look for a new type of material that can offer better mobility, especially compared to materials like the transition metal dicoxygenide for electronics application, and also smaller band gap compared to the TMDCs for infrared optoelectronics. The question is, does such 2D material exist? So that's the question we have in mind when we start to look for possible candidate materials about 3 years ago. And that's when we come across this very interesting book published in 1977 that has listed all the materials with these layered structures that has been studied before that time, right? Of course, at that time, people does not have the concept of thin film material or 2D material. They all look at these materials from the perspective of a bulk material. But nevertheless, the book can serve as a kind of useful database for looking up all these materials with the layered structures. And among the hundreds of material that's in this book, there's one that really catches our attention, and because of the interesting property, that's black phosphorus. So here I show the crystal structure of black phosphorus in a bit more details. You can see that just like a graphene, BP is a layered material. And within each layer of black phosphorus, the phosphorus atoms forms 6 atom rings, just like a carbon in graphene. However, because the phosphorus is a group 5 element, so it has 1 extra valence electron compared to the carbon in graphene. So that gives rise to this puckered orthorhombic structure, where within each layer of BP, the phosphorus atom really stays on 2 separate planes and it goes up and down like this. And we typically refer to this direction of the crystal as the x direction of the crystal, and the direction that's perpendicular to the plane of this slide is the y direction, and the out of atom plane direction is the z direction of the crystal. The material belongs to the D2H symmetry group, which is a lower level of crystal symmetry compared to materials like graphene that belongs to D6H point group. So this is a picture of a bulk single crystal black phosphorus. BP in its bulk form has a direct band gap of 0.3 electron volts, and if you push it down to atomically thin samples, you can tune the band gap all the way from 0.3 eV to above 1.3 eV optical band gap. If you add a little bit of strain, you can push it even further. And the material is also pretty decent electronically. In our first work, we measured the whole mobility at room temperature around 600 centimeters square per volt second. And at a low temperature, that's in the literature, in the bulk form, you can get above 50,000 mobility. Nowadays, the room temperature mobility can easily go above 1,000 in black phosphorus-based materials. And also, the material has strong optical responses in the 1 to 5 micron wavelength range, corresponding to the 0.3 eV band gap it has. It's very interesting for exploring infrared optoelectronic devices. Yes.
Is that a natural material or something that you really have to make?
That's does not.
If I go to a
Yeah.
mountain in Switzerland where I pick up a rock.
Yeah, it doesn't exist often in nature. It's typically people make it from red and white phosphorus, and go through a high pressure process, gigapascal level high pressure process, go through the phase transition. Yeah. Also one of the unique features of this material is that the low level crystal symmetry gives rise to very strong in-plane anisotropy in its electrical, optical, and also phono activities, which may be utilized to develop some conceptually new kind of devices for electronic and photonic device applications. I will show a few examples in later slides. So with that, it comes to the overview of my talk today. So in this talk, I would like to discuss a few of our recent projects in studying the basic electrical and optical properties of black phosphorus, and also in exploring it for electronic and photonic device applications. I'll also briefly mention about the ongoing work in my group in looking at the fractal dimensionality self-similarity in atomically thin materials like graphene. And in the last part of the work, I will talk about a new topic we have started to work on in developing 2D materials for some neuromorphic electronics applications. Some of these new device ideas also make use of the anisotropic properties in black phosphorus. So this slide here summarizes our earlier work in 2014 and 2015. These are some of the earlier studies of the optical and electronic properties in the thin film black phosphorus. That's about between 5 to 20 nanometer, kind of 6 samples. This is a measurement of the extinction spectrum as anisotropic, and the anisotropic DC conductivities, Hall mobilities, and also demonstration of one of the very first transistor devices based on these materials. And more recently, we have been working with our collaborators in the Army Research Lab, IBM, and also at Yale in demonstrating the first black phosphorus transistor that can work into the gigahertz frequency range for high-speed electronics applications. So in this device with a channel length of 300 nanometer, we see FT in the device which characterizes the current gain cutoff frequency of the device is at 12 gigahertz, and the Fmax, which characterizes its power gain cutoff frequency, is at 20 gigahertz. This is pretty decent performance for a new material and the first try. These are the silicon device will perform similarly for similar channel length of 300 nanometer. And we also run the small signal equivalence circuit simulations to really kind of predict how far this material technology can bring us in terms of frequency performance in transistors. We predicted that if we can shrink down the channel length to about 30 nanometer, we can push both FT and Fmax above the 100 gigahertz mark. So in our ongoing work, we have been working on boron nitride, black phosphorus, boron nitride kind of sandwich device structure, in which we measured the mobility above 1500 at the room temperature and over 10,000 at low temperature. And we're aggressively scaling down the channel length of the transistor, and we hope to push both FT, Fmax above 100 gigahertz in this device structure, because boron nitride can be a very good protection, provides very good encapsulation to preserve the high electronic integrity of the BP material. And one of the most unique feature of the carrier dynamics in black phosphorus is that it has a very strong anisotropy, right? Basically, the carrier effective mass along the x direction of the crystal and y direction of the crystal differs by a factor of 10. It's 10 times smaller along the x direction. So carrier moves a lot faster along the x direction compared to the y direction. So in this work, we have been using a newly developed technique, the scanning ultrafast electron microscopy, to sort of directly visualize this whole process in both the spatial and temporal domains, like making a movie. This is a collaboration with Professor Ahmad Zawal's group at Caltech. We started the collaboration in January last year. Very unfortunately, Professor Zawal passed away in August last year. But we have been continuing the collaboration with his postdocs and with the participation of other faculties from Caltech. So basically what the system they have built is that they have integrated an ultra-fast laser with SEM, right? So they basically have a ultra-fast laser source coming out. It's split into two. So one of them is the pump laser, and the other being go through a few frequency multiplication stages to ramp up the photon energy, and is used to excite the filament source in the SEM that generates the electron beam. So the result is that you have a time-correlated and you can have the time resolution to hundreds of kind of femtoseconds level. Time correlated signal of the pump laser optical signal and a probe signal, which is the electron beam, right? So the measurement is very similar to the traditional optical pump probe measurement, right? But the difference is that with the new technique, you get much better spatial resolution, right? So basically, the traditional optical pump probe measurement, the resolution of the imaging is spatial resolution is limited by the spot size of the laser that you use to probe the sample, and that's on the micrometer, right? Micrometer scale. While for this technique, the spatial resolution is only limited by how good your SEM is, right? So that's in the nanometer scale resolution. So you get much finer details, much better details of the carrier dynamics you're imaging. So in this work, we just applied it to black phosphorus and look at its anisotropic carrier dynamics in both the spatial and temporal domain. This is a BP sample. We use the Raman spectroscopy to identify, this is the X direction of the crystal, this is the Y direction of the crystal. And then we load the sample into the SEM chamber. We shine the pump laser, which comes at an angle. So you can see the spot is kind of elliptical, right, because the laser comes from the side. And then the laser strikes on the sample. What you're imaging is the secondary electrons you are collecting from the secondary electron detectors, just like in the SEM imaging you usually do. So the laser strikes, it generates the free carriers, and the carriers are going to diffuse. This is a hot carriers. It's going to diffuse in all different directions. So as time goes by, you can see that the carrier diffuse much faster along the X direction of the crystal and a lot slower along the Y. So you can see this spot kind of expanding more along the X direction and much less along the Y directions. So these circles are just to guide your eyes. And then we turn the sample by 90 degrees. So now the X direction is along here, and Y direction is along here. And then we shine the pump laser, and we let the carrier to diffuse. You can see now the carrier moves much faster along this direction, which is still the X. So the spot elongates faster along the X direction and much less so along the Y direction of the crystal. And these are just images we selected at a particular time, but we have taken, between these two images, we can take like 100 more images in between, right? So we have been able to make a whole movie of this whole process in both the spatial and temporal domain. And this technique is very useful because from this imaging data, you can get a lot of very useful information about the hot carrier diffusion process in all the directions of the crystal, right? So we have been able to extract, the diffusivity along the X and Y direction, the factor of 10 to 15 difference. So these are the hot carrier diffusion shows that it's more kind of related to the ratio of the effective mass in these two directions. While for near equilibrium transport, like if you measure the mobility that's heavily influenced by the scattering, it's only a factor of 2 difference in these two directions. And we can also extract, for example, the carrier recombination time, which is 550 picoseconds in this material. And the diffusion length, the recombination length, is about 9 micrometers along the X direction of the crystal. So these are all very useful information if we were to build these optoelectronic devices. And we use the parameter to simulate back just the carrier diffusion process, and it agrees well with the images we are seeing. And so as I mentioned, one of the key benefits of this new technique is that you get much better, much higher spatial resolution in the images, right? So this is a kind of ideal technique for looking at carrier dynamics through, for example, lateral heterostructures or homojunctions, or through the grain boundaries, how carriers go through the grain boundaries, which is previously impossible if we use the optical pump probe measurement. You just don't have the resolution to see that. Here you are at the nanometer scale resolution. So, and also the technique, of course, it doesn't just apply to black phosphorus or 2D material. It applies to all different material systems. So Professor Zawal's postdocs, they have been looking at silicon PN junctions, how carrier goes through the silicon PN junctions, and also in 3-5 heterostructures. And my group is more focused on the 2D materials. We are looking at the lateral heterojunctions of graphene and molybdenum disulfide with a sample provided by Professor Jin Kong's group from MIT. So we are looking at how the boundary affects the carrier transport. And also we are looking at some perovskite material to really map out the carrier diffusion length, which they claim is over 100 micrometer long. Yeah.
So these are at room temperature, right?
These are at room temperature, yeah.
And then the presumption is the phonon scattering or intrinsic things are limiting the numbers rather than impurity here.
Right, yeah. Yeah. So we hope to have more to report in a few months' time. And so far I've talked about mainly the transport properties and carrier diffusion in thin film black phosphorus samples that's around like 20 nanometers thick. The natural question to ask is how does the material perform optically, and what happens to these properties, right? The optical property, for example, when you get to very thin layers of black phosphorus. So in this work with our collaborator at the Yale and the University of Washington, we have been looking at the anisotropic exciton behaviors and the optical properties in single atomic layer of black phosphorus. That's BP in its true form of 2D quantum confinement. Right? This work is led by our collaborators. We contributed to the sample preparation and some of the data analysis. So I wouldn't go into the details of the work, but I would just like to summarize what's interesting from this study. So the most interesting thing we see is that in our photoluminescence measurement, no matter how we polarize the incident laser, the emitted light, the PL, is always strongly polarized along the x direction of the crystal, and almost nothing coming out along the y direction, right? So this kind of reminds us about the optical property of one-dimensional materials like a carbon nanotube, right? But essentially, basically what we have here is like a quasi one-dimensional material where the physical geometry still looks like 2D, but the optical property resembles that of one-dimensional materials. In 1D materials, it's because the one-dimensional confinement of carriers. In black phosphorus, it's due to the low level of crystal symmetry, because a similar kind of property behaviors, but very different fundamental physics. Yeah.
Yeah, the amazing thing is it looks like it's really zero.
Yeah.
Zero,
Yeah.
zero, zero.
Yeah.
Why is that?
Yeah, it's well, we can simulate the wave function and everything. There's also exciton involved here. It's pretty well with our simulation results. Yeah. Yeah, the level of anisotropy is stronger compared to like the thicker samples. The monolayer is even more anisotropic. Yeah. And another important result from this study is that this is kind of the first time, one of the first measurement, experimental determination of the optical band gap in black phosphorus, single atomic layer of black phosphorus, and also the exciton binding energy. The absorption band gap is around 1.33 electron volts. The exciton binding energy is pretty large. It's 0.9 electron volts, but that's on the same order as materials like molybdenum disulfide. Also, so the electronic band gap or quasi-particle band gap is 2.23 electron volts. So when we go from bulk black phosphorus to single layer, the optical band gap can go from 0.3 eV all the way to 1.33 eV. So this kind of highlights the potential of the material for, and it's always direct band gap. So it highlights the potential of the material for infrared optoelectronics application. Because with just one material, it can cover a very significant portion in the mid-IR region, and also most of the near IR regions. So in order to realize that potential, recently we have been working with our collaborator at Yale in demonstrating a black phosphorus mid-IR detector that works in the 3 to 5 micron wavelength range. So the 3 to 5 micron wavelength range is a critical wavelength range for many military technologies, like especially the night vision system the Army is using. The incubant technology for 3 to 5 micron detection is sort of based on mercury cadmium tellurides, the MCT-based detectors. These are very good performance detectors, but you need a kind of liquid nitrogen cooling for it to work well, and it's very difficult to integrate that with the silicon electronics. So with black phosphorus, we hope to have a solution that that's easy to integrate with silicon, and can also operate at room temperature with decent performance. We are not looking to exceed the performance of MCT, but we hope to have a performance that's good enough for some of the applications. So in this work, we demonstrated a BP detector that can respond to 3.39 micro wavelength lasers, right, the light. And we see the responsivity of 100 amp per watt. This is very decent performance at this kind of wavelength at room temperature. The detector is not very fast. It works in the kilo. This kind of responsivity is maintained up to about kilohertz frequency. So it's definitely not fast enough. If you want to use these detectors for like a free space communication, it's not fast enough. But for imaging and sensing imaging applications like night vision, it's more than enough. For night vision systems, the human eye, for example, can only respond to like 60 hertz per frame rate, right, per second. Also, the black phosphorus detector gives the added benefit, that's the unique polarization sensitivity. Now, because the material has very different optical responses along different crystal direction, so the incoming light that's polarized along the x direction of the crystal or y direction of the crystal will give you very different photocurrent in the detector. So the detector will not only be able to tell whether there's incoming light or not, but it will also be able to tell you how it's polarized, how it's linearly polarized. And that's very useful because when you have an object you are imaging, you are looking at, the light reflecting off any object surface will kind of become polarized anyway, corresponding to how the object surface is being oriented. So by knowing the polarization information, you can kind of infer some 3D geometrical information or the orientation about the object you have been looking at. So if we can build night vision systems like with black phosphorus, the soldier will not only be able to see the object there, but they can also infer some 3D shape about the object they are looking at, and also the orientation about the object. So that's something we are very interested in. Army is interesting, so something we have been working on right now. Also, besides the 3 to 5 micron wavelength range, we're also developing black phosphorus for the 8 to 12 micron wavelength detection. That's for thermal imaging applications. The 8 to 12 micron is another critical wavelength for the military technology, especially used by the Air Force in their weapon system that utilizes the thermal checking and imaging. So in order for black phosphorus to make black phosphorus be able to detect these photons at longer wavelengths, at lower energy, we have to reduce its band gap. Right? 0.3 eV corresponds to like 4 microns. It's too large of a band gap for this range. So we have two different approaches. We're working on two different approaches. One is by alloying black phosphorus with arsenic element. So arsenic is also a group 5 element. So you can start from a black phosphorus, and you can replace the phosphorus atom with arsenic atoms. The more arsenic atom you put in, the lower the band gap goes. So in our previous characterization, we see that when we have 83% arsenic content, the band gap goes to around 0.15 electron volts. So that's around 8 micron wavelengths, and you can go even beyond that. And currently, we are working on some device-level demos for long wavelength detections based on these materials. And the second approach we have is the simple electrostatic bias and creating the Stucky effect to cause the effective narrowing down of the band gap. So in year 2015, there's this group in South Korea that published this paper in Science. They basically what they did is they doped the black phosphorus surface with potassium ions, charged potassium ions, right? So these charged ions creates the vertical electric field that induces the band gap narrowing. So you can see as the electric field increases, as the potassium ion doping level increases, the band gap in black phosphorus reduces from 300 millieV all the way to 0, right? So these are not simulations. These are actual APAS mapping of the band structure. The band gap basically narrows down and becomes sort of a derived coin kind of shape at a very high electric field. However, the doping-based method is not very attractive for device applications for two reasons. Firstly, these dopants are not very stable. You heat up the sample a little bit, these dopants will be gone, right? So that's not attractive for device. And also, by doing this doping, you lost the dynamic tunability. You basically, you can dope the sample, you can cause the band gap to reduce, but you get a fixed band gap after that. So in our work, we have been working with our collaborator in sort of demonstrating that's the same effect, but through just electrostatic gating, right? Just by building an electrode underneath. So through the transport measurement and also some tight binding modeling, we have been able to see that if we increase the electric field from 0 all the way to 0.9 volt per nanometer, this is the displacement field. So the actual electric field will be divided by epsilon, right? So if we use like dielectrics, like aluminum oxide, epsilon is like 7 or 8. So the electric field needed is about 0.1 or 0.2 volt per nanometer, which is about 1 order of magnitude less than the breakdown field in this dielectric material. So these are reasonable electric fields that can be easily achievable in regular dielectrics. So when we go from this increases this electric field, we see the band gap, effective transport band gap, goes down from 300 millieV, that's 0.3 eV, to 60 millieV. So that corresponds to the 4 micron wavelengths all the way to 20 micron wavelengths. So you can, with just one material, you can cover both the 3 to 5 micron wavelength range and also the 8 to 12 micron wavelength range. And the response is tunable both dynamically and continuously, right? So this can be very interesting for exploring some new type of device applications for both night vision application or thermal imaging application, especially in cases, in applications where the dynamic tunability is desirable, right? So here I would also like to mention ongoing work we have in looking at the Hausdorff dimensionality and self-similarity in atomically thin material, basically graphene. So if you take a sheet of graphene, we can pattern it using these many different levels of self-similarity patterns, like the triangles here and the squares here. And in principle, if we do that in infinite number of times, the resulting Hausdorff dimensionality or fractal dimensionality will be given by this mathematical expression here. So for example, for this pattern, you will get a dimensionality of 1.58. So it's not something that's not 1D or 2D, it's somewhere in between, right? So of course, the strict mathematical definition requires infinite level of cutting, which is not possible. But for applications, for example, in microwave or in optics, as long as the wavelengths of these signals are much longer than the features in these patterns, the unique properties will arise, right, due to this fractal dimensionality effect. So for a practical device application, we are working on a graphene-based, this tunable fractal antenna. This is a collaboration with Northrop Grumman Corporation. They are interested in this type of fractal antennas for their airplane communications in the 5 to 20 gigahertz frequency range. So these are pretty large centimeter scale kind of antennas. And the researchers at Northrop Grumman has helped us with the simulation of the antennas with just 2 levels of self-similarity patterning. We're already seeing some unique modes or combination modes that's due to the fractal dimensionality effect. Also, the graphene has a tunable carrier density. So these modes, these frequency responses are also dynamically tunable by the gating effect. So the simulation is all done, and we are currently working on fabricating these antennas and testing it at the Northrop Grumman facilities. Yeah.
So what does it buy you to have a fractal dimension as opposed to say 2? What's a triangle compared with Hausdorff?
Yeah. So it's the you can kind of estimate with the log 3 to log 2. The 3 is kind of the filling factors. So the filled part with the unfilled part in each level kind of ratio.
I was thinking as an antenna, why would I buy this one instead of just having that triangle?
Oh, you will have some modes that are unique, that are not available with the normal kind of geometry, or combination of modes that are not possible to have. Yeah. In the last part of my talk, I would just like to talk about a new direction we are working on in developing 2D materials for neuromorphic electronics applications. So this slide kind of summarizes our motivation for working on that. So basically, if we compare our human brain with the von Neumann computing system, that's the computers or the servers we have today, we can see that our brain can sort of perform about 7 order of magnitude synaptic events. That's the number of computations per second compared to the von Neumann computing system, and consume only 4 order of less power. It runs on about 10 to 20 watts of power, our brain. It's like a light bulb at home. And so there must be something we can learn from our brain when designing the next generation computing systems. So the key difference between these two architecture lies in the fact that for the von Neumann system, the memory parts are largely separated from the CPU, the processing unit. So there's a lot of traffic. This link between the memory units and the CPU chips, they become the bottleneck for both the speed and also a lot of that that raises the power consumption for performing certain tasks. So, for our brain, the computational units, which are the neurons, and the memory units, which are the synapses, they are very closely coupled with each other in a highly parallel way and in a 3D kind of integrated structure, right? So it's this high-level parallelism that gives our brain many advantages over the computers in processing tasks that requires parallel processing, like image recognitions or a lot of the learning and clustering algorithms. So it's desirable if we can mimic some of these functionalities in the computing system. But however, it turns out that our current hardware platform is inadequate for realizing functions like our brain. So there are two different approaches people have been working on for quite a long time in building neuromorphic electronic system. One is a circuit-based approach. This is purely based on the CMOS transistors. So basically build circuits that can mimic the functions of the synapse and neurons. So the downside of that is that you need typically around 10 to 20 transistors to mimic the function of one synapse, and you need a lot more transistors to mimic the function of a neuron, right? So the circuit complexity and power consumption will just go up exponentially as the system becomes more and more complicated. So it's desirable to have one device to mimic one synapse, right? So that's why people are working on the device approach, and there are two different classes of devices people are working on. One is a FET type kind of charge trapping memory type of devices, and the other type is the resistive memory type of devices, include like oxide memristors, phase change memory devices, and spin torque transfer type of memory devices. So these devices can mimic one synapse with one semiconductor device, but the problem is that they can only also mimic the most simple version, while the biological synapses have very diverse functionalities. They can reconfigure between excitatory and inhibitory mode. They can make new connections and destroying existing ones. So in order to mimic all these, we need a new type of material properties and new devices. And we feel that the 2D materials has a rich array of unique physical properties that could be interesting to sort of try to explore some of these applications. So in earlier last year, we have demonstrated the first black phosphorus-based artificial synaptic devices, and also utilized the phosphorus oxide layer as a charge trapping layer to realize the synaptic functions. The synapses are functional links between the neurons through which the information flows throughout the whole neural network, and they vary very differently from each other in terms of their connectivity from one to the other. It's this heterogeneity that gives rise to very diverse functionalities of brain, from the imagination to memory, from logic to reasoning. So it's desirable to mimic this heterogeneity in the connectivities. And it turns out that it's not so easy to do so in the solid-state systems, because you need some intrinsic properties that's in the device that's different from one device to the other, and just changing the geometry, the shape of the device is not going to work. So here in this work, we propose to build these devices along different directions of the crystal of black phosphorus to take advantage of the different intrinsic transport properties along the different directions to realize this heterogeneity. So I wouldn't go into the details due to the time constraint. We basically characterize able to demonstrate the typical synaptic characteristics in the device, the potentiation, the depression, and also the spike time independent plasticity, which characterize the time correlated kind of effects between the input and output signals in influencing the synaptic weight of the link. One of the key features we can see that for devices built along X and Y direction, we see very different characteristic profiles. Not just one point, but the whole profile is very, very different along these two directions. Yeah.
How does this like a memristor, or is it
This is more a charge checking, more like
Okay,
a
so
flash memory type of device.
The BP is tracking charge.
Yeah, the phosphorus oxide is tracking the charge.
I see.
Yeah, it's influencing the
If
conductivity.
you pulse it up, then you pump it more.
Yeah, this is more like a 3-terminal kind of device.
So STDP is not just unique to resistive memory, so it can happen with the charge trap.
In the FET type also.
Okay.
Yeah.
So how many devices like this could you possibly integrate on a chip?
We build like for this particular flake, because we only have small flakes of black phosphorus. So we build this radio shape, for example. It can mimic like a simple network with one axion connected to multiple synapses. For if you want a dense array, you need a larger material area, and have to consider how to lay out this radio shape circles across a large wafer. Yeah, we haven't get to that point yet. But so we're able to mimic the a simple network with one axion connect to multiple synapses, and this kind of network can be, or the devices can be very useful for enhancing kind of level of complexity and also the functionalities in neuromorphic electronics. So here I would also like to talk about a more recent device we have been building. That's a gate-tunable kind of memoristic device that can mimic the heterosynaptic behavior. So a memoristor is basically a different type of device that can be used for memory application and for synaptic operations. Basically, it has two electrodes, metal electrodes, and sandwiching a layer of median layer in between. Typically, an oxide, transition metal oxide, and could be other materials as well. You can apply a bias between the two electrodes and can create a conductive filament path between these two electrodes, and the device will be in the conducting state, and you can reversibly break this filament, so it will be in the non-conducting state. So that will give you the 0 and 1 state for data storage, and you can use that for memory application. And companies like HP and also Micron, they have been pushing very hard for this technology as one of the possible options for future memory chips. And also you can operate these memoristors or resistive memory devices in the shorter pulsed mode, and then you can control the size of this filament in much finer steps, and you can control the conductivity of the device in much finer steps. You have much more different levels of conductivity, and you can operate that as a synaptic device. So in our work, we made a bit of modification to the traditional memoristor devices using 2D materials. So instead of using two metal contacts to make the device, we replace one of the contacts, in this case the bottom one, with a piece of graphene. So graphene is a semi-metal, so you can use it as a contact. You can inject carriers to this median layer. And the good thing about graphene is that because it's extremely thin, this is single-layer graphene, we can build also a gate underneath. The gate electric field can sort of penetrate through the graphene layer and influence the whole filament formation process in the median layer. So now we have two different electric fields here. We have the gate electric field in the vertical direction, and also the bias field between the top and bottom electrodes that's also in the vertical direction. So if these two electric fields are aligned with each other, you're going to enhance this filament, conductive filament formation in the oxide median layer. And if the gate field opposes the bias field, it's going to suppress this filament formation process. If the gate field is much larger and also opposes the bias field, you're going to dominate over the bias field, and you can get inhibitory responses. So the device has a very good analogy in the biological synapse systems. That's the heterosynapse. So this is the schematic of the usual kind of homosynapse. You have the presynaptic input and the postsynaptic output, and you can mimic the operation of these synapses with like a regular memoristor devices. But our device sort of resembles more of this heterosynapse structure. You have the usual synaptic device, synaptic connection, but you also have a neuromodulator that can release neural substances that will influence the performance characteristics of the whole profile of performance of this synaptic link. So and this type of device, this type of synaptic structure is very important actually in neural computation also, because they are kind of the analogy of transistors in the neural network. So here is the IV characteristics for our device with the gate grounded. So there's no gate field applied sorry, it's grounded. So you can see the typical memoristic kind of IV characteristics in the device. And this figure is kind of interesting. It shows how the gate bias can influence the set voltage of the synaptic of this memoristic device, this memoristor. The set voltage is the voltage you apply between the top and bottom electrode at which this complete filament forms and the device becomes conductive. So for negative gate biases, the two fields are aligned with each other, the gate field and bias field, and it enhances the filament formation process. So that's why your the set voltage is lower. So when the gate bias becomes less negative to 0 or even positive, the gate starts to oppose this filament formation, and the filament is more difficult to form. So the set voltage has to be higher than previously. So this kind of already gives you an indication about how this gate field can influence this filament formation process. So in these slides, I show our characterization of the key synaptic characteristics of the device. So you can see that for a negative kind of gate bias, the two fields align with each other. It enhances the filament formation. So you get a strongly excitatory kind of responses in the pulsed mode. And when the gate bias kind of becomes 0 and slightly positive, it starts to sort of suppress this filament formation. So the response becomes much lower. When the gate field becomes very positive, gate bias becomes very positive, the gate field will dominate over the bias field. So you get the inhibitory responses. So you can see that in this device, we can use the gate to dynamically tune the operation of the device between the excitatory mode and the inhibitory mode also. And within each mode, the response is also tunable. So here we also characterize the spec time independent plasticity for both the excitatory mode and inhibitory mode. For the excitatory mode, the data is in the first and third quadrant. For the inhibitory mode, it's in the second and fourth quadrant. And within each mode, is a time constant for the correlation is also tunable in these devices. So this kind of device is very useful for enhancing functionality, also enabling reconfigurability for the neuromorphic electronic systems. So with that, I think time's almost there. I would like to come back to this slide that summarizes my talk and the various projects I've discussed. I would just like to say that the black phosphorus is not the only low symmetry duty material out there. There's also material, like the arsenic alloys of black phosphorus, and also materials from the group 4 element monocalcotonides with materials like germanium selenide and tin selenide that also have this low symmetry structure, and also the low symmetry members of the 2D crystal, 2D transition metal diconchanide family like ramine disulfide, ramine diselenide. Now, all these material has the anisotropic electrical optical properties. Also, their low-level crystal symmetry also gives these materials some very unique properties, like the giant piezoelectric coefficient over 200 has been predicted theoretically for the single-layer tin selenide, and also the polarization tunable kind of plasmonic resonances in black phosphorus. Also, some ferroelectric properties are starting to be studied theoretically recently. So, and they can have many potential applications in electronics, in photonics, in ferroelectrics, and in the piezoelectronic systems. I also want to say that the research in the field of low symmetry 2D material is really in the infant stage, at the beginning stage. I showed some early simple, the characterization of the material property, and also some simple demonstration of some device ideas, but really everything is still yet to be done. Right? There will be many challenges, of course, as we move forward, but I also see plenty of interesting opportunities lying ahead of us with this family of material. So with that, I would like to conclude my talk. I would like to thank our students who contribute to this work, our collaborators at Caltech, our Muri team members at MIT, and also here at Harvard. Also, especially Professor Millie Dresshouse, who gave us a lot of guidance and support over the years. So very unfortunately, she passed away recently. And also our collaborator at the Yale, University of Washington, in Washington University, St. Louis, and also in government research labs like ARL, and also Argonne National Lab, and industry partners, Northrop Grumman and IBM Research, and our funding agencies for supporting all our work. So thank you.
detection.
Yeah.
So in the beginning of your talk, you with this optical pump electron probe technique, you measured a carrier recombination time around picoseconds, hundreds of picoseconds.
Yeah.
But then the response time of the photodetectors was something like kilohertz.
Yeah.
Do you have some sort of explanation?
Yeah. So the response time of the detector are more trap dominated. So these are more like time scale of the trapping and detrapping states. That's the main limit for the speed instead of the at the beginning. So the measurement in the ultrafast spectroscopy is like the pump signal is at a much higher energy. Also, it's in the 500 nanometer kind of range wavelength. So it's a green laser. While for the detector, it's 3.4 kind of micron lasers. So yeah.
For the fractal planar waveguides, I didn't understand why it's special to have these unique modes that arises from the reduced dimensions or the fractional dimensions.
Yeah, it comes from the fractional dimension.
But I don't understand why are these unique modes special.
Yeah, it basically when you have different patterns in these waveguides, you affect the distribution of all the EM field that's around it. So with the unique pattern, you have
What are
the.
they useful for? I guess is my question.
Yeah, it depends on what kind of modes you're looking for and what kind of combination of modes you are looking for. Northrop Grumman won't tell us what exactly they want it for, but they're interested in these tunable antennas and tunable fractal antennas, and also they're interested in kind of reconfigurable antennas that can change the shape and things like that.
Synapse functions a live area of research. Do you have any input from the folks who are trying to figure out what's various sorts of synapses and how they function?
Right. So here for these devices, we are just mimicking the simplest kind of functions of these synapses. We do talk to people in the biology department and people doing brain-related research who to look for other kind of functionalities of the synapse that they would like to have. But also we have to talk to the people in the computing side. What are the functionalities useful for building the computing? The synapse has a lot of different functions, but not all can be easily used for building computational architectures. Yeah.
One last question? Okay, if not, let's thank Tom again.
Thank you.
Okay, and people who are signed up